Okay, everyone, let's begin then. Probability is what we are going to do today. We're done with some concepts. We started discrete random variables in the last session as well, but I gave you more time to practice probability. So you could do more questions from the worksheet and then let me know the problems that we're having today. So let me know any questions that you guys have from the worksheet or otherwise from any of the recent papers that you might have attempted. And we will start doing them one by one, inshallah. Gee, everyone, please post your questions so I can decide the order in which we're going to do them in. So I would want to do them in increasing order of difficulty. So let me know all the questions. I'll list them down and then do them one by one, inshallah. Gee, no other questions apart from these? No other questions apart from these? Sure. Okay, chale. Let's start with some of these questions then. Let me look at them and then decide the order in which we're going to do them. S1, probability. $44, okay. 30, 33. Okay, all of them look like average difficulty, at least from the marks and the statements. Let's just do them randomly then. Question number 3, let's start with this. Okay, acha, I understand. Remember I told you to skip questions involving mean and variance for now, right? We can't consistently use combinations for these. What do you mean by these? Acha, this question number 30 is actually something that you can skip for now. If which part of this is what you have a problem in, because the last part is binomial distribution and the second part is also binomial distribution. So only the first part we can do. I think that's pretty straightforward. So second and third parts are binomial distribution, okay? So any questions that in this worksheet that involve mean or variance, you can skip them for now, as I said before. So 30 we cannot do for now because we have not done binomial distribution, okay? So we will be done with that tomorrow actually. Tomorrow we're doing binomial distribution. After that, you will find that this is actually pretty straightforward using binomial distribution concepts, okay? So 30, you can skip for now. Let me read this again. 33. Okay, this we can do. Let's have a look at this. Question number 33 from the worksheet. Let's start with this one. Yeah, these are not very difficult, so it's okay. We'll go through the basic concepts using this as well, right? Probability is not that difficult overall as a topic as well. So let's start with this. Two identical biased triangular spinners with sides marked 1, 2, and 3 are spun. Okay, so we have triangular spinners. We have these sides that are marked. They're both identical. For each spinner, the probabilities of landing on the sides 1, 2, and 3 are PQ and R respectively. So what that means is probability of 1 is P, probability of getting a 2 is Q, and probability of getting a 3 is R. The score is the sum of the numbers on the sides on which the spinners land. Okay, so you are spinning two spinners at the same time. The score is calculated like this, that you would just add up the two numbers that you get, right? You just sum up the two numbers that you get. What we're given is, let me actually just highlight this so we know what we're talking about. Probability that score is 6 is 1 over 36, and the probability that score is 5 is 1 over 9. We're given these two probabilities. Find the values of P, Q, and R. Okay, now when can we get a score of 6? When is a score of 6 possible? Which outcome will give us a score of 6? P3, right? That's the only possibility. So 3 is when the score is going to be 6. So what's the probability of score being 6? How many total outcomes do we have? 3 on the first spinner, 3 on the second. The total number of possible outcomes, that is going to be 9. Can I just do 1 over 9? Will that work? Can I do 1 over 9? Can I say the probability of getting a score of 6 is 1 over 9? Will that be correct? That's clearly not correct because this is 1 over 36. How do we calculate this probability? Remember, all sides do not have equal probabilities. So that number of favorable outcomes divided by total number of possible outcomes, that formula would only make sense if each outcome had equal probability. Now, in this case, 1, 2, and 3, they have different probabilities. That's why we cannot just say divide the favorable outcomes divided by the total number of possible outcomes. That would not work. 3 and 3, its probability is just going to be probability of getting a 3 on the first outcome. On the first spinner is R, and on the second spinner is also R. So we're just going to do R times R. R on the first spinner, R on the second spinner. That's the probability. They are saying this probability is 1 over 36. Just equate it to 1 over 36 and you get R squared equal to 1 over 36, and you can get the value of R from this. You can see what that is. R equals 1 over 6. Can it be positive? R represents, can it be negative? Sorry, R represents probability. So we will only consider the positive value. So R turns out to be 1 over 6. So this is one value that we have figured out. R is 1 over 6. Okay. Now let's talk about a score of 4. How is a score of 4 possible? A score of 4 is possible if we get 2, 3, or if we get 3, 2. Right? These are the two possible outcomes. That will give us a score of 5. 2 on the first spinner, 3 on the second spinner. 3 on the first spinner, 2 on the second spinner. Now, what is this probability going to be? Probability of score being equal to 5. Now, what about 2, 3? 2, 3 would be Q into R. Q on the first spinner, R in the second. So that will be QR. Or you could have the second outcome. That will be R times Q. That's basically the same, right? Two numbers are multiplying. The order is irrelevant. And that is going to give us the result. We add both of them and that gives us 2QR. Okay. Now, they told us that this probability is 1 over 9. We equated to that. And now QR turns out to be 1 over 9. Now, we already know the value for R, right? We can input that here. Input the value of R here and it will become Q into 1 over 6 equal to 1 over 9. And the value of Q turns out to be 6 over 9, which is 2 over 3. So we got the value of Q as well. Okay. So we found the value of R and the value of Q. What else? What about P now? Can you find the value of P now? What is that going to be? What's the value of P going to be? Yeah, yes, I'm sorry about that. When you divide 2 on the other side, it's going to be 18. This should have been 18 here. 2 was divided on the other side, right? So it should have been 18. That's 6 over 18. That's 1 over 3. Yes. Sorry about that. So we got the value of R and the value of Q. Yeah, sorry about that. So I fixed that. Achha. What about P now? How do you find the value of P? How do you find the value of P now? The total probability is going to be 1. Since the total probability is 1, all we have to do now is subtract the other probabilities from 1. Subtract the other probabilities from 1. Okay? And throw a side पे हो जाओ. 1 में से minus कर दें. And that will give you the result. Let's do that quickly. Subtract from 1 the other values. Okay? Let's see what we get from that. There has been a problem here at my end. I'm just trying to fix that quickly. Why did we multiply both R into R? What do you mean by that? In the first case? In the first case? Because we have 2 spinners, right? We have 2 spinners. The probability of the first spinner having a value, first spinner giving us 3 is R. Probability of second spinner giving us 3 is also R. So we have R from the first spinner, R for the second spinner. So we multiply them, right? Yes. Sure. यहाँ पे actually थोड़ा सा पानी गिर गया है, so I'm just trying to save my laptop and my iPad. Okay, I think it should be fine now. Achha, so how do you find the value of P then? What about the value of P? P is going to be 1 minus 1 over 6 minus 1 over 3. And you can see what that turns out to be. What do we get from this? What's this value? Anyone? 1 over 2? All right. This is the value of P that we end up getting. Okay, that was this question. Let's move on. Let's move on to the next one. That was 6 marks, not that difficult if you understand what they're asking about. It wasn't that complicated, right? Achha. Let's move on to the next one now. After 33, the next one that you asked about was 44 and 21. Okay, let's try those now. 44. Let's look at question number 44. Okay, now it says one plastic robot is given away free inside each packet of a certain brand of biscuits. It's 44, right? Yeah. There are 4 colors of plastic robot. red, yellow, blue, and green. And each color is equally likely to occur. Nick buys some packets of these biscuits. Find the probability that he gets a green robot on opening his first packet. Okay, now since each color is equally likely to occur, what's the probability going to be of the first packet being any color? Just 1 out of 4 because they're all equally likely. Just 1 out of 4. So that's pretty straightforward, the first part. 1 out of 4. I was just checking if it's binomial or geometric. The second part is actually geometric, but we can just do it logically as well. The second part we can just do logically as well, even though we don't know what geometric distribution is at this point. Let's look at the second part. Find the probability that he gets his first green robot on opening his fifth packet. Now, this is from 2015. We did not even have geometric distribution at that point. So we can do it without that as well. But just thinking of it logically, they're saying the first time he gets a green robot is when he opens his fifth packet. What that means is he should not get a green robot on the first packet, not on the second packet, not on the third packet, only gets it on the fifth packet. What is that probability going to be? So first robot is not green. What's the probability of that? 3 out of 4. First is not green, right? Then what's the probability of the second robot not being green? That is also 3 out of 4. Third not being green, 3 out of 4. Fourth not green, that's also 3 over 4. And then the fifth is green, so that's 1 over 4. So that basically simplifies to 3 over 4 raised to power 4 into 1 over 4. Just put this on a calculator and you get a result from this. You can see what that is. Make sense, right? G. What do we get? 0.079101. 0.079101. Three significant figures become 0.0791. And that's our final answer. Okay, that's the second part. Again, that's pretty straightforward. What about the third part now? Find the probability that the first 4 packets he opens all contain different colored robots. They should all be different colored. They should all be different colored. What about this now? So the first he opens, whatever that color is, that color should not repeat. So for example, if the first is red, then the second may be yellow, then the third may be blue, and the fourth may be green. What's the probability of getting red? 1 over 4. Yellow, 1 over 4. Blue, 1 over 4. And green, 1 over 4. Right? This won't work. What's the problem with this? What's the problem with this? Because all of them have 1 over 4. So what would not work? So this is just one possible path that we could have on the tree diagram. So if you think of the tree diagram for this, you could say the first robot he gets, it could be red, yellow, blue, or green. Then the next robot after that could be red, yellow, blue, green, red, yellow, blue, green, and so on. And then the next one after that, again, red, yellow, blue, green. We've got 4 possibilities again, 4 again. That becomes 4 raised to power 4. That's too many cases. 4 raised to power 4, that's 256. So we can't really complete this tree diagram. But we can just think of it like we did yesterday for those questions, if you remember. This question, remember? So we thought of the tree diagram and we said, okay, how many possible paths like this exist on the tree diagram that would give us all different colors. So for example, one possible path on the tree diagram could be that we get red on the first one, yellow on the first one, a second one, blue on the third, green on the fourth, right? But then what happens afterwards? There are other possibilities as well. For example, you could have yellow, red, blue, green. You could have blue, yellow, red, green. How many such possibilities exist? There are four different colors. We can arrange them in how many ways? 4 factorial ways. So we multiply this by 4 factorial, and that will give us the result. There are 4 factorial such paths on the tree diagram that will give us 4 different colors. So for that reason, we multiply by 4 factorial, and that should give us the answer. You can see what that turns out to be. Okay. What do we get? 3 out of 32. 3 over 32. You can leave it as it is if you want. It's just a probability. Or you can write it in decimals as well. That's also fine. Now, will the combination method work here? We don't really have anything to choose from here. What's the total number of colors, as in how many red colors do we have to choose from? Well, we just know the probability, right? That probability of getting a red color, yellow color, blue color, green color. So the combination function needs some total number, right? NCR. So we can't really use that idea here. So in this case, we had all different objects, 12 different peppers, and we had different colors that we had for them. Here we just have one of each color. So that is why I said you should know this other method as well, because sometimes this is all that you can use. The combination method is not going to work in all such questions. You should know this tree diagram method as well, in which you find the probability for one possible path and then multiply that with the possible paths on the tree diagram like this. Any problems? No? Okay, let's look at the next one. Next one in the list was 21. You can also post other questions if there are any other that you have problems in. I'm doing 21 next after this. 21. Let's try this. Okay, again, they're talking about mean number of toffees taken, probability distribution table. But we have done discrete random variables, right? We've done discrete random variables, so we could do this, right? 21. Let's try this. 21. We know what a probability distribution table looks like now. So we should be able to attempt this. 21. 4 factorial नहीं समझ आया. अच्छा, let me repeat this. Let's take a smaller example. That's a useful thing to think to do. If you can't understand what's happening in a bigger problem, convert that to a smaller problem. So let's suppose I had just two things, black and white. Or let's suppose three things, X, Y, Z. Now, first time I have three options. I can select one of X, Y, and Z. Second time, again, I've got three options, X, Y, Z, X, Y, Z, X, Y, Z. Third time, I've got three options, X, Y, Z, X, Y, Z, X, Y, Z. And then, sorry, secondly, these are the options that we've got second times. Then the third time as well, we've got three options further with each one of them. Now, if I want the probability of having all three different objects in these three selections that I'm doing. Now, one possible way of doing that would be that I say I select X the first time, Y the second time, and Z the third time. So this is one possible path that I have on the tree diagram that will satisfy the condition. X the first time, Y the second time, Z the third time. Now, the only condition was that we wanted X, Y, Z selection for the three letters that we are selecting, that all three letters should be different. Now, one possible way of having all three different letters is that we have X the first time, Y the second time, Z the second time. Are there other paths on the tree diagram that would also give us three different letters? There are also other paths that will give us three different letters. For example, one other path would be we have X the first time, Z the second time, and then Y the third time. That's another possible path. Another possible path could be we have Y the first time, X the second time, and then Z the third time. That's another possible path. And then we could have Y, Z, and then X. That's another possible path. And similarly, you'll have two more. So how many such paths exist on the tree diagram? How can we find them? They will be equal to the number of ways in which we can arrange X, Y, and Z. We can arrange X, Y, and Z in 3 factorial ways. So we multiply by 3 factorial. Now, in this case, the tree was even bigger. We had four objects that we were selecting. So we can't really show the whole tree diagram. We just said one possible path on the tree diagram that will give us all different colors is RYBG. That's one possible path on the tree diagram. How many paths exist on the tree diagram that will give us all different colors? That will be equal to the number of different ways we can arrange these four letters. That will be the number of paths that exist on the tree diagram like this. So in how many ways can we arrange these four letters? 4 factorial ways. That is why we just multiply this by 4 factorial. That's the reason we did permutations and combinations first, so we could understand problems like these when we do probability. Okay, that's how we approach this. Okay, we discussed this in the last session as well. You were there, I think, Sharyar. Let's have a look at this one now. Okay, now they're saying Mariam has 7 sweets. Mariam has 7 sweets, and 6 of them are toffees, one is a chocolate. She chooses one sweet at random and takes it out. Her friend adds 3 chocolates to the 10, then Mariam takes another sweet at random out of the 10. Draw a fully labeled tree diagram to illustrate the situation. Now, even if they had not asked you to do this in the first part, you would still do it because otherwise the next parts would become difficult, right? So to do the second, third, fourth parts, it would have been a good idea to make the tree diagram anyway. But let's do it now. They asked you to make that tree diagram. Now, the first time she chooses one sweet, what are the options? She could get a toffee or a chocolate. What are the probabilities? 6 out of 7 for a toffee, 1 out of 7 for a chocolate. Then what happens is the friend adds 3 chocolates to the 10. So next time, what are the probabilities? She could have a toffee or a chocolate, toffee or a chocolate. The number of toffees is unchanged, as in they're not adding any more toffees. If you took out a toffee the first time, the number of toffees that is left is 5 now. What about the total number of sweets? We had 7 initially. We took out 1 and then we added 3. 7 plus 3, that's 10, minus 1, that is 9. So the second time she picks out a sweet, there are 9 sweets inside that container. 5 out of them are toffees. What about the number of chocolates? There was one chocolate already. She added 3 more. So that's 4 out of 9. If she took out a chocolate the first time, the number of chocolates that is left now is going to be 3, the 3 that were added later out of 9. And then the number of toffees, what about that? That is going to be 6 out of 9. That's what the tree diagram looks like. Okay, makes sense, right? That's O-level stuff. There's nothing complicated there. The first part, okay. Achha. Let's have a look at the next part now. It says draw up the probability distribution table for the number of toffees taken. Now, what are the different possibilities for the number of toffees that you could take out? You could take out 0 toffees or 1 toffee or 2 toffees, right? These are the only 3 possibilities that we've got. Part 2. So we could say we have a table like this. Have they used any variable there? No. Let's call this variable something. Let's call this variable x, or you could also call this t if you want, number of toffees. I'm representing number of toffees by x. Okay, so now there are 3 possible values of x, 0, 1, or 2. What are their probabilities going to be? 0 toffee, that means chocolate into chocolate, right? This will be the 0 toffee case, which is 3 out of 1 over 21, right? It will simplify to 1 over 21. This is going to be 1 out of 21, right? The first one. 2 toffees. What about this? We multiply these two. 6 into 5. 30. We can do some cancellation as well. Has anyone done this? 10 over 21? Okay, thank you. 10 over 21. That's for 2 toffees. For 1 toffee, you would have to consider these 2 cases, this one and this one, and add them up together. But if you're sure that these calculations are correct, then you can just write down this one directly as well. Subtract from 1 this number and this number, and that will give you 10 out of 21 as well. Although it's a good idea that you calculate it yourself, so that then you can verify that your answers are correct by summing them up. If they add up to 1, that most likely would mean that your answers are correct. Okay, so this is what we end up getting. That's the probability distribution table. The third part says find the mean number of toffees taken. That's just sigma xp, right? We have done this. We did this in the last session. Discrete random variables, mean of x. How do we calculate that? That's sigma xp. Add another row to the data, which represents xp, which is going to be 0, 10 over 21, 20 over 21. If you add up all of them, they're going to give you 30 over 21, which is 10 over 7. That's the mean value. You can write that in decimals as well. In decimals, that turns out to be 1.43 to 3 significant figures, right? That's the third part. That's also pretty straightforward. Any problems until this point? Any issues until this point? No? Achha. Let's look at the next part now, part 4. Next, they're saying find the probability that the first sweet taken is a chocolate given that the second sweet taken is a toffee. Now, that's a conditional probability. Remember the conditional probability formula. It looks like this: probability of A given B, that is equal to probability of A intersection B divided by probability of B. In simple words, in the numerator, we have the probability of both events happening together. And in the denominator, we have the probability of the given event. Okay? Achha. So what is it that they're asking about? Probability that the first sweet is a chocolate, first is a C, given that the second sweet is a toffee. Now, what does the formula say? The formula says we are going to need the probability that first is a chocolate, and at the same time, intersection means and, right? Both things should be happening together. And second is the toffee. That's the numerator where both things are happening together. And then in the denominator, we would have the probability that the second is a toffee. That's what we would have in the denominator. Now, how do you find these probabilities? Look at the tree diagram. First chocolate and second toffee. Chocolate, toffee. What's that going to be? The numerator, it will be 1 over 7 into 6 over 9. That's the numerator. Chocolate and then toffee. The denominator is that the second should be a toffee. Now, second could be a toffee in two different ways. You could have chocolate toffee like this, or you could have toffee toffee, right? Both of these cases, we will have to add them up together. So we will say the denominator is going to be these two multiplied plus these two multiplied. What I'll do is I'll just do these calculations here in the tree diagram so it becomes easier for you to understand. So I'm multiplying these two, 6 over 7 into 5 over 9, and that will give us something. You can see what that is. 10 over 21. We actually calculated this earlier as well. This probability. And then CT, what's this? 1 over 7 into 6 over 9. This would be 2 over 21, right? 2 over 21. So all we have to do is in the numerator here of this fraction, we have chocolate toffee, which is 2 over 21. And in the denominator, we've got the sum of these two numbers, which is going to be 10 over 21 plus 2 over 21. And that is going to give you the result. You can see what that is. It will be 2 over 12, which is 1 over 6. And that's your final answer. Okay. That was not very difficult. It was probably extremely straightforward, this question. The second part, Hamad, did you attend the last class? Did you attend the last class? Yesterday's class? No. So this is a discrete random variables concept, probability distribution table. This table is, the table means that you just have two rows like this, in which in the first row, you write down the possible values of the variable that you've got. In this case, they were talking about number of toffees. Now, what could be the number of toffees? It could be 0 or 1 or 2. So we write that in one row, and in the second row, we write down the corresponding probabilities for them. So what's the probability of 0 toffees? That will be this no chocolate. That is when you have 0 toffees, right? So when we multiply these two, 1 over 7 into 3 over 9, this gives us 1 over 21. That's why we've got 1 over 21 here. Two toffees means multiply these two. That gives us 10 over 21. That's what we've got here. And similarly, the middle one, that will be the sum of the second and third cases. The second case would be 6 over 7 into 4 over 9, which simplifies to 8 over 21. So sum of these two numbers, that's 10 over 21. That's what we've got here. Okay. Did you really find nothing else difficult in the probability worksheet? No other questions? Okay, let's just do one more then, and then we end for today. What I'll do is I'll choose one myself then. Let me look for a difficult question. Okay, there are actually a couple of questions, or maybe more than a couple, which are fairly complicated. Let me just do a couple of them then. Okay, so we are not going to end after one question. Let's do a few more than one. Okay, let me start with this one. Question number 27 from the worksheet. Question 27. Let's try this. Now, this one is fairly complicated. Has anyone attempted this yet? No? Okay. So let's have a look at this. 27, and then we'll do one more at least, or maybe two more. I'll at least show them to you quickly. One that I want to do after this is 29. This also is slightly complicated. And then this question 52. Okay, let's just do these three questions and then we end for today, inshallah. Let's start with this one. This is probably the hardest of them all. In a group of students, the number of toys and the number of boys, I'm sorry, not number of toys, number of boys and girls studying art, music, and drama, they're given in the following table. Each of these 160 students is studying exactly one of these subjects. Find the probability that a randomly chosen student is studying music, right? So they have put together all the useless subjects in one question. Find the probability that a randomly chosen student is studying music. Now, what is this probability? Acha. So all such questions in which they give you a table like this, the first thing you should always do is you should have row totals and column totals added to the table. And that will help you with your calculations. Add row totals and column totals. Okay. So in this case, 24 plus 15, that is 39. 40 plus 12, that is 52. 32 plus 37 is 69. Add row totals. What are they going to be? 32 and 24 is 56, and that's 96. And then 27 and 37, what's that? 50 plus 14, which is 64. And then you have the grand total here. Did they give you the grand total? Grand total must be 160. So this grand total here, this has to be 160. So add these totals that they will help you with your calculations. Okay. Find the probability, first of all, they're saying out of these 160 students, find the probability that a randomly chosen student is studying music. Now, what's that probability going to be? We are selecting from these 160 students. What's the probability that a randomly chosen student studies music? 52 over 160, right? The total number of students studying music is 52. Divide that by the total number of students, that's 160. So that will be 52 over 160, right? That's straightforward, the first part. This is what we get from this. Okay, what about the second part now? Determine whether the events a randomly chosen student is a boy and a randomly chosen student is studying music. Determine whether they're independent or not. Now, what do we know about independent events? How do we know if two events are independent or not? Two events are going to be independent if the probability of their intersection, probability of A intersection B, is equal to probability of A into probability of B. You need to remember this condition. Okay. That's the condition for independent events. What we can do is we can say a randomly chosen student is a boy. Let's call that B, probability of B. So all of them have different starting letters, right? B, G, A, M, D. Yeah, okay, so that should work. We can say one is probability of there being a boy, and the other is probability of music. We have to find these two probabilities and then the probability of their intersection, which will be probability of B intersection N. Now, what are they going to be? Probability of a randomly chosen student being a boy. Out of 160, how many boys do we have? 96. So this probability is going to be 96 over 160. Probability of a randomly chosen student studying music, we already calculated that before, that's 52 over 160. What about the intersection? Probability of a randomly chosen student being a boy and studying music at the same time. Boy and music, that's these 40 students, right? Out of how many? Out of 160. So this probability is 40 over 160. Now we need to check if they satisfy that condition or not. So what we can do is we can put them in this equation for them to be independent. Probability of B intersection M. This should equal probability of B times probability of M, right? Let's check this. Intersection probability is 40 over 160. Probability of B is 96 over 160. Probability of M is 52 out of 160. Simplify them on the left side, we get 1 over 4. Put this on your calculator and see what that gives you. What do you get from this? The right side? Anyone? 0.195. What's the fraction? 39 over 200. 39 over 200. So that's clearly not equal. So we can say these two are not equal. If they're not equal, that means they are not independent. Okay? So they're not independent. That was the second part. Okay? Now that was also not very difficult. What about the third part now? Find the probability that a randomly chosen student is not studying drama given that the student is a girl. Not studying drama given that she is a girl. That's conditional probability, right? This is also straightforward. So we are given that the student is a girl. That means we are only talking about these students, right? We're only talking about these students. So the total number is going to be 64. It's a conditional probability. The denominator is not going to be 160 anymore. The denominator is going to be different. The denominator is going to be different, right? Okay. Given event is that it's a girl, so we are only selecting out of these 64 students. Out of these 64 students, what's the probability that the student does not study drama? That's these 27 people, 15 plus 12. So this conditional probability, therefore, it's going to be 15 plus 12 over 20, sorry, over 64. And that's 27 over 64. Now, we have not used the conditional probability formula here. You could also use that if you wanted. That would be probability of the given event in the denominator. If the given event is in the denominator, the given event is that it's a girl. What's the probability of that? Of a randomly chosen student being a girl? That's 64 over 160. That's the denominator. Then the numerator should be where both of these things are true at the same time, girl and not studying drama. That's this 15 plus 12, 27 out of 160. So what happens is we have 15 plus 12 divided by 160. 160 and 160 get cancelled if we were to use the conditional probability formula, and we would end up with the same thing, that's 27 over 64. So if we were to use probabilities, the 160 and 160, they would get cancelled and we would end up with the same number. So when you have a table given, finding conditional probability is easier just from the table directly, right? So we were given that it's a girl, so we are looking at these 64 students. Out of them, 27 satisfy the condition and that gives us the result. That's how we normally do it in SAT, where we do not study the conditional probability formula explicitly, but the idea is tested. So from the table, we just do the calculations like this. Okay, makes sense, right? For mutually exclusive events, the condition is that intersection should be equal to zero. For independent events, the condition is intersection should equal the product of their individual probabilities. And we discussed logically what both of them mean in the last session as well. Mutually exclusive means if one event happens, the other cannot happen. Independent means if one happens, the probability of the other remains unaffected, remains unchanged. Right, that's the second part. Now think about the last part. Let me know what to do with that. Take a minute, think about that. Let me know what we should do in that third part. Three students are chosen at random. Three students are chosen at random. Find the probability that exactly one is studying music and exactly two are boys. How do we think about this now? Exactly one is studying music and exactly two are boys. That's a 5 mark question. What's the complication here? Tree. How would we make a tree for this? Okay, so let's suppose we make a tree diagram. What would the tree diagram look like? What do we have in each step? So we are selecting the first student. What are the possibilities? What are the possibilities for the tree diagram? Combinations. How would you make combinations? That could actually make sense. Using combinations in this case, because we're selecting and the total number is fixed, so combinations would actually be the easier way of doing this. How do we use combinations? In this case, we can use combinations because we know that we are selecting three students and it's without replacement. So we know how many we have in each category and how many we need to select, right? But there's a complication there as well. Sharyar, what happens to you around 10 p.m.? You start using some other language all of a sudden. Yeah, I'm just trying to read. Even your typed words are looking extremely small to me, like your handwriting. Okay, how do we think about this? Okay, let me know what the complication is. Let me know what the complication is. The complication is There's an overlap between these two categories, right? There's an overlap. What's the overlap? If we select one student who is studying music, now it is possible that that one student is chosen out of these 40 students. And if that is the case, then the total number of boys is going to reduce. And these two boys that we are choosing, they would have to be selected from a smaller number, right? So the number of boys that we are choosing from, that is going to reduce in that case. That's the problem. So how do we handle that problem now? How do we handle that problem? We consider two scenarios. We consider two scenarios, or maybe three. Let's figure that out. We want exactly one student to be studying music. So what that means is that student that is studying music, it could be out of these 40 students. That's one possibility. Or that could be out of these 12 students. That's another possibility. We would have to make separate cases that either that student that we are studying, who's studying, that the student that we are selecting who's studying music is whether that's a boy or a girl. Because that is going to change what we can do for the selection of boys then. Let me write that down. One case could be that the three people that we're selecting, they look like this. There is one boy who is studying music. There's one of these people. And then if one boy is what we have selected here, then what about the other two people then? There could be total two boys, right? So for the other people, there would have to be one boy who is not studying music. There should be one person from those people, and then one girl who is not studying music. There should be one from those people, right? I'm not going to read the chat right now. Let's focus on this, and then I'll look at your suggestions as well. This is one possible case. This ensures that the total number of boys that we have got in the three people that we're selecting, that is one, that is two. So we have one boy who is studying music, another boy is not studying music, and a girl who's not studying music. That's one possible case. Now, the other possibility could be that the student who's studying music is a girl instead. So we could have a girl who's studying music. Okay. Now, if the girl is the one who's studying music, then both the boys that we are selecting, they should not be studying music. So the boys who are not studying music, we need to select two out of them. These are the two cases that we end up getting. We wanted two total boys, and the total number of students studying music, that should have been one. These are the only possibilities that we get. One possibility is in which the student studying music is a boy. If we start with that condition, then we need one boy who's not studying music and one girl who's not studying music. The second possibility is that we have the girl who's studying music. Then the boys that we are selecting, they should both be not studying music. These are the two cases that we get from this. Okay. Now, what are the possible selections for both of them? The first case, number of boys who are studying music. What's that? 40. We want one out of those 40 students, 40C1. Okay. And one out of students who are not studying music, one out of boys who are not studying music. 24 and 32. What's that total? 56. Out of those 56, we want one. And then one girl who is not studying music, how many of them do we have? 15 and 37, that's 52. So we multiply this by 15, 52C1. That is one possibility. The other case is girl studying music. What's that? That's 12. We want one person out of those 12, 12C1. And then boy not studying music, 24 and 32, that's 56 people. Out of those 56 people, we want two. This is going to give us some combinations. We can see what they turn out to be. The first one is just 40 into 56 into 52. That's 11,6,480. The second one is going to be 12 times 56C2, and that is 18,480. Now, what's the probability going to be then? The probability is going to be the favorable combinations, which are 116480 plus 18480 divided by the total number of possible combinations. That means where we have no condition, there are 160 total students. If there were no conditions, we could select them in 160C3 total possible ways. Put that on your calculator, and that should give you some number, plus 116480. Divide this by 160C3, and that is what this probability turns out to be, which is 0.20146. To three significant figures, that's 0.201, and that's your final answer. Does that make sense? Yeah, that needed quite a lot of thinking, I think, not just some. This is one way of doing this. The other way of doing this could be that same idea, thinking of a tree diagram and then finding one probability of one case, multiplying that by the number of arrangements for them. That will be a slightly more complicated method. You could try that as well, but this is already pretty complicated. I think this is better. Okay, ठीक है. No, instead of that, we'll do another question. Have a look at this again in your own time. This was a good question. If you were to make a tree diagram, that you will also have to make that using cases like this, right? So it'll be like you're selecting 3 students, right? So you'll have cases like this. You have so the two things that matter are boys and music, right? So you can have boy music, boy not music, girl music, girl not music. That will be your first step. And then you'll have the same steps further, right? Boy music, not music, girl music, not music. So it will continue like this. Yeah, but then you do those permutations method, right? Arrangements method. You find the number of possible cases. So one possible case in this case would be BM, and boy music, we want only one music. So BM, BM, B not boy not music, and girl not music. That will be one case in this case. And then the other case would be girl music, boy no music, and boy no music. These will be the two cases. You find the probabilities, Find the probability of this case. These are all different. Whatever this probability turns out to be, you multiply this by 3 factorial. In this case, we've got two identical. So we multiply this by 3 factorial over 2 factorial, right? Yeah, the first one will multiply by 3 factorial and this one by 3 factorial over 2 factorial. And remember, this is without replacement. So the denominators are going to change every time. So yeah, it's going to be a bit complicated. Thank you for that, Musa. That's good to read. Now let's look at the next question. That was 27. Let's do the next one now. Question number 29. I had to go to a dinner today, and I delayed that for you guys because I did not want to miss the class. And you guys are already sleepy. Question number 29. I still have to go after this, Abhi, but I want to do this question as well. Okay. A fair tetrahedral die has faces. Tetrahedral, that's four-sided. You must have seen that. Four-sided, it's like a pyramid, right? It has faces numbered 1, 2, 3, 4. A coin is biased so that the probability of showing a head when thrown is 1 over 3. The die is thrown once and the number n that it lands on is noted. The biased coin is then thrown n times. So for example, if the die lands on 3, the coin is thrown 3 times. Why can you guys not think? Tetrahedral dice. This is what it looks like. Right? Not exactly. Uh, that has 5 sides. Toblerone has 5 sides. This is 4. Yeah, okay. Chale, let's do this question. Find the probability that the die lands on 4 and the number of times the coin shows heads is 2. Now, what does that even mean? Read the question statement. Okay, now focus here. Read the question statement. Read the question statement and try to understand what they're saying. It's a fair die, numbered 1, 2, 3, 4. The die is fair, but the coin is biased, and the probability of head is 1 over 3. The die is thrown once and the number n that it lands on is noted. Now, n could have these possible values. It could be 1, 2, 3, or 4, right? The biased coin is then thrown that number of times. So if if the dice shows 1, you toss the coin once. If the dice shows 3, you toss the coin 3 times, and so on. We need to find the probability that the die lands on 4. Now, what's that probability that the die lands on 4? That's 1 over 4. And the number of times the coin shows heads is 2. Now, probability of the die showing 4 is just 1 over 4. So that's easy to work with, right? Probability of getting a 4, that is 1 over 4. Now, if you get 4, how many times are you going to toss the coin then? 4 times. Out of that 4 times, what's the number of times that the coin shows heads, we have to find the number of times that the coin shows head. We have to find the probability for that. Now, what would the tree diagram look like for this? You could also do this using binomial distribution, by the way. Those of you know that. We will discuss that later and then in tomorrow's class, inshallah, but we can do it without that as well. It's not that complicated. So the first time you toss the coin, you have head or tails, right? The next time, again, you've got head or tails, and then you've got head or tails. And then similarly, it keeps going on like this, right? Head, tail, head, tail, head, tail, head, tail. Now, keep this example in mind. We'll do something similar for binomial, understanding binomial distribution tomorrow as well, inshallah. This is what happens the third time. And then similarly, the fourth time, you get something. Acha. Now, they want that the number of times the coin shows heads, if that is 2, what's the probability of that? Now, if there are 2 heads, what does that mean? You want head, head, and then tail, tail, right? Now, they could come in different orders on the tree diagram. They would come in multiple different orders, right? This is what is this? This is one possible path that we could follow on the tree diagram, H, H, T, T. That gives us 2 heads. There could be other paths as well, for example, head, tail, or head, tail, tail, head. How many paths exist on the tree diagram like this? 4 factorial divided by 2 factorial and 2 factorial. Right? That's the number of possible paths that we've got like this on the tree diagram. Again, we've done something like this before as well. What's the probability of getting heads the first time? Probability of heads was given to be 1 over 3. Then again 1 over 3. Tails 2 over 3. Tails 2 over 3. That's one possible path on the tree diagram. We multiply by the number of possible paths. Over 4, that's 6. 6 into 4, that's 24. No, that's not 4 over 27. That's actually 4 over 81, Sharia. That's 4 over 81. Multiplied by 24 over 4, which is a 6, and that simplifies to 8 over 27. So this gives us 8 over 27. So the probability that they were asking about now, that the die lands on 4 and the number of times the coin shows heads is 2, what's that probability? We multiply these two cases, and that's 1 over 4 into 8 over 27. And that will give us something that will be 2 over 27. That's the probability. Okay? Makes sense, right? No problems? Now, these are some of the more difficult questions. That's okay. If you were confused about them initially, it's generally going to be easier than this. That was the first part, okay? Now let's look at the second part. Ji Ahmad. The second part says find the probability that the die lands on 3 and the number of times the coin shows heads is 3. Now it's very similar to what we did before, right? Probability of the die landing on 3, what's that going to be? 1 over 4 into the number of times the coin shows heads is 3. How many times are we tossing the coin in this case? Since the die landed on 3, we are only tossing the coin 3 times. What's the probability of having all heads? That will just be 1 over 3 into 1 over 3 into 1 over 3. That's only one possible path, right? That all of them are heads. There are no arrangements for this as such. And that will give us the result. You can see what that is. 1 over 27 into 4, that will be 108, and that's the probability. Okay, the second part was fairly straightforward. Yes, Amar, please go on. Okay, let's complete this question and then we'll end with this. You can ask verbally then. Let's just do the third part. Do you have a question on this question or something else? On this question or something else? Okay, जी बता. You can unmute then. Let me know. You can unmute and speak after that, not just unmute. I can't hear you. Can anyone hear me? Hear him? Ahmad की आवाज आ रही है किसे? Ahmad, you had to speak after unmuting as well.
सर अब आ रही है आवाज एक्चुअली
ठीक है.
मेरा हैंड फ्री का माइक कनेक्टेड था खराब है
Yeah, it's okay. जी बताएं.
सर तो जब हम हेड हेड और टेल टेल किया यहाँ पे हमने 1/3 फिर इंटू 2/3 तो वी मेड अ पाथ मतलब हमने दिखाया कि यार ये एक केस हो सकता है एंड देन वी मल्टीप्लाइड दैट बाय 4 फैक्टोरियल ओवर जो भी 2 फैक्टोरियल इंटू 2 फैक्टोरियल शो किया कि यार इतने डिफरेंट पाथ एग्जिस्ट करते हैं राइट
Yes.
हाँ बस ठीक है थैंक यू सो मच सर
Okay. Oh yeah. All right. That's good. That was the second part. Let's look at part three now. Let's look at part three. Find the probability that the number the die lands on is the same as the number of times the coin shows heads. The number the die lands on is the same as the number of times the coin shows heads. What does that mean? That if the die shows 1, then you get 1 head. If the die shows 2, you get 2 heads, and so on, right? So you can think of it like this. You can say the number that the die can show, it could be 1, it could be 2, it could be 3, it could be 4. Then the coin in the first case has to show 1 head, in the second case 2 heads, in the third case 3 heads, in the fourth case 4 heads. What's this probability? That if the die shows 1, you get 1 head. If it shows 2, you get 2 heads because you're only tossing the coin 2 times as well, and so on. Now that's straightforward because what's the probability of getting 1 on the dice? It's 1/4. And you are tossing the coin only once. What's the probability of getting a head? Probability of head was given to be 1/3. So this will be 1/3. Then the next time probability of getting a 2, that's 1/4. What's the probability of getting 2 heads after that? 1/3 into 1/3, that will become 1/3 squared. In the third case, probability of getting a 3 is 1/4, and then 3 heads, toss the coin 3 times. What's the probability of getting 3 heads? That will be 1/3 into 1/3 into 1/3, that's just 1/3 cube. And then finally, probability of getting 4, that's 1/4, into probability of getting 4 heads, that's 1/3 into 1/3 4 times, that becomes 1/3 power 4. And now it's either the first case or the second case or the third or the fourth. We add up all of these cases and that's going to give us the result. The first one is 1/12. The second one, 1/12 times 1/3, that will be 1/36. The third one will be 1/108, and the fourth one is going to be 1/108 into 3, that will be 324. And then you add up all of these cases, that will give you the result. You can see what that is. What's the final result that we get from this? If you add up all of them, ten over 21. Okay. 10 over, sorry, 10 over 21 or 81? 10 over 81. Yeah. Okay. 10 over 81. That's the final answer. That's what we were looking for. Okay. Well, actually, a lot, Mosa, but currently I'm just drinking water. I don't drink tea. I don't like tea, which is odd in my family, but I don't. 52. Okay, this was pretty straightforward. Now I'll recommend that you try a couple of more questions at least. A couple of other specific questions at least. For example, question number 52. Note it down if you haven't already. Question 52. Note it down. Make sure that you attempt this. 52 from the worksheet. 52. And then there was another that I had in mind. Mm, Try this. Question number 79 from the worksheet. 52, 79. Do try these questions if you haven't already. 79, this is a good question. And there was another here as well. Yeah, 76 is another good one. 76. Do try this as well. 75 as well. 75. 63. Okay, so you can try more as well. This is also really good, but we already attempted that 29 or 27, I think. Yeah, that should be okay. So these 5 questions, at least make sure that you try them in your own time later on. Tomorrow, we are continuing with binomial distribution, inshallah. Okay. That's it. I'll see you in the next class then. Allah Hafiz. Yes, there is a class tomorrow. There is a class tomorrow because we missed our Monday class, right? We missed our Monday class. So we are going to make up for that tomorrow, inshallah. Okay. So tomorrow we're doing binomial distribution. Allah Hafiz. Same time, yes, same time. Allah Hafiz. Bye. Thank you.